The second question is a decimator. So before we look at this question, let's look at the one slice to just review what happens if you downsample a signal. So in this case, you start with a 6K hertz signal, okay? And that's the signal because based on the Nyquist sampling theorem, so if you have a 6 kilohertz sampling frequency there, so the maximum the highest frequency you can have in that signal is 3 kilohertz. Okay, so that's the one. So if you directly downsample it by factor of 3, so make it a 2 kilohertz, there will be a problem. Okay, because you will have this higher frequency will fold back into the lower frequencies. That's called a aliasing problem. All right, so we need a anti-aliasing filter. So this is the filter here. Okay, that is a anti-aliasing filter. All right, so the filters look like this, and actually this question is asking us to design this filter. So this original signal xn go through this filter, it will become the result here. So that's the spectrum at Wn. All right, and then you can safely downsample it by 3 times. So it becomes 2 kilohertz. 2 kilohertz is here, and this is Nyquist frequency. So it will be mirrored against this half of the sampling frequency. And as always, if you look at more samples, it will mirror itself multiple times. Okay, this one up to 6 kilohertz, it will mirror itself as well, right? We just didn't draw it there. So that's give you enough motivation. You need an anti-aliasing filter so that you can safely downsample it to avoid aliasing problem. Okay, so if we know that, let's look at this problem. How to design those filters. So in this case, we need to do a 2-stage decimator. Okay, we're gonna downsample 2 times, and to determine the pass band, stop band, and other and order of the anti-aliasing filter of each stage. Okay, so the whole things look like this. So we start from the input sampling frequency is 96 kilohertz. Okay, so it goes in. So we need the first low pass filter number 1. Okay, we need that. After this low pass filter is still 96K, and then we do a decimator, the first stage. Okay, after this first stage, it's become 3K, right? 32 times smaller, and then we need another low pass filter or anti-aliasing filter. Then it's still 3K. Then we do another decimation. Then it's finally become 1K. Okay, that's the output. All right. So to do this one, we need several parameters. So delta P and delta S, the pass band attenuation rate ripple and stop band ripple are these 2 numbers, and delta F. Okay, and delta F is normalized transition width. We need to find it for each filter. Okay, let's look at the first filter. So the first filter is low pass filter number 1. Okay, low pass filter number 1. So what we do know is the pass band area is 450 hertz. Okay, because the pass band frequency is this. So what we don't know is this one. Okay, we don't know. This is the stop band. You can see the stop band edge frequency for this stage. Okay, so Fs number 1, the first one, is equal to capital F1 minus Fs divided by 2m. Okay, Then we will talk about what's of this each parameters. So F1 here is the output sampling rate for this stage. For the first stage, the output is 3K. Okay, so we got this one equals to 3K minus Fs is 96. Okay, is the system basic sampling frequency, 96K over 2M. M here is 96 because 32 and 3 multiply 32 and 3, so that is 96. So if you do the math, 3K minus this, you got this one equal to 2.5K. So this one is 2.5K. Then we can do the normalized transition. So to normalize it, we need to do that delta F equals to 2.5K, okay, minus 450 divided by the sampling frequency, which is 96K. Then if you do the math, you got this equal to 0.0214. Okay, that's pretty much okay. We know this F and this delta stop. There's no problem. The pass we need to separate. Sorry, we need to divide it by 2 because there are 2 stages. Okay, you can imagine a signal go through one stage. It will be attenuated because that's passing band. It's really gonna affect the useful signal. So we're gonna separate this to 2 parts. So the SP hat equals to 0.01 divided by 2 because there are 2 stages. Okay, 0.005. That's the answer. So for the low pass filter number 1, the order gonna equals to -10 log the passing band ripple 0.005 multiply with 0.001. That's stop band, and -13 divided by 14.6 multiply with the delta F we just got 0.0214 and plus 1. Then you will get the answer is equals to 129. Okay, then you can pause here and try yourself, see if you can get the second one. Okay, so for second low pass filter number 2, again it's look like this, and the passing band is still 450, and we just don't know what is this F stop band number 2. Okay, this one gonna equals to, we're gonna use that equation again. Okay, so that's the system. First is F2, right? F2 is the output sampling frequency at this stage will be 1K. Okay, and minus a Fs, still the basic sampling frequency, and 296. Okay, then this one is 500. Okay, so the delta F is 500 minus 450 divided by 96K, and this one we got 0.0167. All right, then you want to plug it into the capital N again, so everything's still the same. So the passing band ripple is 0.05. All this are the same. The only difference for second one is you replace this one with this one, then you will find the result equals to 165. Okay, so in summary, then we can get the result. Filter number 1 is the passing band frequency is 450, the stop band frequency is 2.5K, and the order is 129. Okay, so based this we can find the filter, we can design the filter. And the filter number 2, the passing band same 450, the stop band here is only 500, and the order is 165. Okay, it makes sense, right? It's a sharp transition, so you need a higher order. Okay, so that's this question. We shrink a little bit so you can see all the steps.